Bismillahirrahmanirrahim. Welcome to the lecture number 5 of chapter number 1. Our today's objectives are: by the end of this lesson, students will be able to know the concept of base E exponential function. They'll be able to know the growth and decay applications. Now, what is base E exponential function? An irrational number symbolized by the letter E appears as the base in many applied exponential functions. It models a variety of situations in which a quantity grows or decays continuously. That is, money, drugs in the body, probabilities, population studies, atmospheric pressure, optics, and even spreading rumors. The number E is defined as the value that 1 plus 1 over n raised to n approaches as n gets larger and larger. Now, what is E? Now we'll study what is E. The base 10 and log to the base E. Why are they most commonly used logarithms? How do we really understand them? Log to the base 10 is kind of initiative. It's easy to talk in multiples of 10. 10, 100, 1000 and so on. Log to the base 10 gives us an easiest way to work with. Log 10 to the base 10 is 1. Log 100 to the base 10 is 2. Log 1000 to the base 10 is 3. And we can see that the multiples of 10 can be managed with the scale of natural numbers. But log to the base E is what I'm deeply interested in. It's called the natural log, and it's also written as ln. Yes, log to the base E is also written as ln. So log 20 to the base E can be written as ln of 20, the natural log of 20. What is this E? Some call it a magical number, some call it an irrational constant, and some call it a Euler's number. But the harsh truth is that very few people actually understand what E is. To get to E, we first need to understand growth. Let's say a particular thing doubles every time period on this timeline. This is today and every unit in one time period. Assume we have $1 with you. At the end of the first time period, this dollar doubles and you have $2. At the end of the second period, $2 doubles to become $4. And at the end of the third period, we have $8. How do we look at this growth? First, we see that the number at the end of the time period are power of 2. It's in the form 2 to the power x, but x is a non-negative integer. 2 raised to 1, 2 raised to 2, 2 raised to 3 and so on. This was one way in which we looked at double growth. Another way to look at it is that there is 100% growth at every time period. 1 plus 100% of 1 gives us 2. $1 was increased by 100% to get 2. In the second time period, $2 grows to $4. 2 plus 100% of 2 gives us 4 and so on. So doubling the value is the same as a 100% increase. So 2 raised to x can also be written as 1 plus 100% raised to x. It's like you were getting 100% return on your investment. But hold on. We are making an assumption here. We are assuming that growth happens in a discontinuous fashion. We are seeing growth in steps here. What about the time in between two time periods? We are seeing no growth in between. So growth and its surrounding doubles. Again no growth and suddenly doubles. But that's not how nature works. Everything or every kind of growth happens gradually. If your height today is 4 feet, you suddenly won't be 5 feet a year later. Your height gradually grows. When we started studying, we used to have 30 students a day. And then after a year, the school grows with the number of students 4,000 a day. It doesn't mean a view count just jumped for one fine day. It gradually increased. So growth in nature is never really discrete or discontinuous. Let's see how it really works. We take the example of $1 growing over one period at 100% growth. First, we look at the annual growth based on what we saw. At time 0, we would have $1. And at the end of the year, we will have $2. This doesn't seem right because all the interest cannot appear on the last date. To make it slightly better, let's divide the year into two equal parts, 6 months and 6 months. Splitting that 100%, the growth would be 50% on the first year and 50% in the second. It would look like this. Our initial dollar earned 50% interest in the first half to give 50 cents more. Now what happened in the second half? $1, 50 cents remains as this growth is 50%. So 50% of $1 will be 50 cents, and this time the 50 cents also earned a 50% interest, that will be 25 cents. This 1.5 is the sum of the original dollars and the 50 cents we made here. So at the end of the first year, we have our original dollar, then we have the dollar that made our original dollar made, and we also have the 25 cents that these 50 cents made. A total of $2.25. This is better than doubling. If you want to understand this using a formula, it would be 1 plus 100% over the whole square. We had half the growth rate over 2 time periods. This is also referred to as semi-annual growth. Let's push ourselves further. What if we had 4 equal time periods in a year? We have divided 1 year into 4 quarters. This is how it would look. Looks messy, but it's actually very simple if you have understood the concept. It's 25% growth every quarter. The formula would change to 1 plus 100% over 4, the whole raised to 4. We would approximately get $2.4 and at the end of the first year. I suggest you pause the video and understand quarterly growth diagram really well. The 100% is nothing but 1. If 2 time periods, then we have 2 here. If 4 time periods, then 4 here. So the formula for n time periods would be 1 plus 1 over n the whole raised to n. Clearly, more the number of time periods high will be the return. This will give us the dollar value at the end. I probably know what our greedy brain is thinking. It is possible to get unlimited money. Let's make the table now. Number of time periods and the dollar value at the end. If it's just 1 time period, the dollar value is 2. If 2 time periods, then $2.25. If 4 time periods, then $2.44. If I divide the year in 12 equal time periods, my return will be higher than this. If I divide it in if I divide it in 365 equal time periods, it will be even higher. This tells us that the dollar at the start of the year will become these many dollars at the end of 1 year. If the number of time periods is 365, so if we increase this number significantly, that is, if we increase the number of time periods significantly, will this number also increase significantly? Okay, here are a few more calculations. The number of time periods here is 1 million. Notice that the return improve. Yes, but they converge around a value which approximately equals to